Welcome everyone. I see a lot of familiar faces, but also a lot of outside people. Very nice to welcome you all to the AI for Wildlife challenge. Final presentations. For the last 10 weeks, we worked really hard to bringing poacher detection machine learning models into production on a wildlife protection drone. For today, we have in store for you my name is Dorian Groen. I'll do the challenge introduction. Then we have 4 of our teams who will be presenting all their progress over the last 10 weeks. First, we'll have Jaka. He will present for the model optimization team. Followed by Aisha, who did the CIC, who will present the CICD team. Then we have Alan, who will tell us everything about the hardware in this challenge. And last but not least, Ryan Wolf, who has spent the last 10 weeks on autonomous flight. And we have here from Spots, Robbie Benninka and Peter Milton as well. They will give us some closing words and a thank you. By the way, if anyone has any questions throughout the presentation, please raise your hand in the bottom to put it in the chat, and then I will ask the questions to the speakers. Okay, let's admit the final people. For the people who are here for the first time with Fruit Punch AI, I'll give a short introduction on who we are. We are Fruit Punch AI. We are building the global AI for good community. And we do this because we believe that to solve humanity's greatest challenges, we need to educate AI engineers at scale with an ethical and sustainable mindset. And how do we do this? We organize AI challenges that are geared towards the sustainable development goals, because we believe that challenge-based learning is the best way of learning AI in practice. We host these challenges, as I said, towards all the sustainable development goals, but we're here today to talk about the goal 15, life on land, where we host the AI for Wildlife challenges. In this challenge, we collaborate together with Spots. They are the strategic protection of threatened species. And here today with us are Robbie Benninka, Peter Milton, and Johan Benade. They spend day and night in protecting the South African wildlife. They do so by flying over the wildlife reserves of South Africa with a fixed-wing drone, as you can see on the right top of the screen. But this can be a very time-consuming and also prone for human error task. That's why we at Fruit Punch AI started organizing challenges to automate this process of poacher detection on the thermal camera view of these drones in order to cover as much land as possible, but also to take a lot of work out of the hands of the rangers in South Africa. Apart from that, I want to give a special thank you to our partners through this challenge. We have RoboFlow provided us with their platform for dataset creation and augmentation. I want to thank Enabler for labeling a lot of the data that we used, and KPI and Accelera AI for their expert knowledge and sponsoring throughout the challenge. So why are we hosting these challenges? In South Africa, more than 1,000 rhinos are slaughtered per year for their horns. Their horns are going for a very high value on Asian black markets. And to battle this, we need to be able to map where poachers are in the reserves of South Africa. And therefore, we are helping Spots to use AI to aid in this poacher crisis. Over the duration of 10 weeks, we had 4 groups working on this topic. We had a total of 26 AI for good engineers who collaborated and together spent over 4,000 hours of engineering work on this challenge. The goal of this challenge was detecting poachers using on-edge machine learning on a fixed-wing drone. And we did this through continuous integration and deployment of machine learning models on edge. We built a streamed video feed and machine learning pipeline. We also focused on model optimization, since we have limited capacity in the on-edge hardware of the drone plus that we need it to be as energy efficient as possible. So model optimization, pruning, and quantization. And finally, automating the flight and landing of the fixed-wing drone to really take most of the work out of the hands of our friends at Spot. Yeah, we've started at the 21st of March, and we are finishing off today with the final presentations. Throughout the challenge, we have also organized master classes and a midterm presentation that maybe some of you were also present at. But that's everything that I have to tell you. Then I want to go into the presentation of our model optimization team. So I would like to invite Jaka to start sharing his screen and yeah, to really get into the details of what kept him busy.
Hi everyone. I hope you can see the slides like this.
Yes, we see your screen.
All right, and if I start the presentation, do you still see it?
Yeah, it works.
Perfect. Great. Hi everyone. I'm Jaka. I'll be presenting for the model optimization team, which consisted of Sahil, Manu, myself, Sabelo, and Sinan. And yes, like Dorian said, we have been busy because our goal was to optimize the model for NVIDIA Jetson Nano, which is the computer that will be running on the drone. And the purpose of our optimization was to increase inference speed so that we can perform as many inferences on incoming images as fast as possible, and also reduce memory footprint, because these low-powered devices have a limited amount of memory there. And if we want to run more than one thing at a time, we need to have the smallest memory footprint possible. More about the hardware, it is here. So you can see this quite a small thing. It has 128 CUDA cores of Maxwell architecture. Just for reference, modern GPUs, for example, now have about 3,000 CUDA cores. And it has about 4 gigabytes of RAM, which is a bit like an old computer. Nowadays, graphics cards also come with 12 gigabytes or even 16. And it also has two power modes, 10 watts and 5 watts, where 10 watts is a super power mode, which overclocks a bit and uses 4 cores, while 5 watt is low powered mode, using only 2 cores and decreasing frequency of GPU and CPU, which is more suitable for the drone to limit how much power we draw from batteries. So we tackled our task by first researching, creating this ideation and splitting tasks. And we figured that the best place to start would be to figure out what is the best model architecture to use and which image size we should input into the model itself. Here we did experiments with image size 640 by 640, 480, 480, and 320, 320. Then we also looked into mixed precision training and tested YOLO v5 using quantization to FP16 as opposed to FP32, which is floating point, and floating point 32 takes basically longer to compute because there are more numbers. And FP16 basically halves that. Quick summary. And then we also explored model pruning, which is supported by YOLO 5 itself, and we explored some other methods for pruning. And pruning is where you basically get rid of some of the weights in the models. You set them to 0 and also try to get rid of a few connections so that you have less compute operations to do. We experimented also with Onyx, which is a popular framework for model optimization, but I won't go into details here to not bore you. And finally, we used Tensor RT, which is NVIDIA's own solution for optimizing models to be deployed on NVIDIA-specific hardware, which I will tell you more about a bit later. So before we jump into what we have achieved, I would just like to say that focus on inference speed here, so the inference times per image, instead of absolute accuracy that we've achieved, because our goal was not to get the best performing model, but it was to Do you still see my screen? Yeah.
Wait, I can still see it, but it's minimized. Wait. Oh, if you pin it, you can see it large again.
Does everyone see my screen? Okay.
No, Jaka, can you reshare it?
Okay, I'll reshare it. Yeah.
Maybe just reshare it indeed.
I don't know what happened. Let's go. Okay, you can probably see it now.
We're back.
So like I was saying, so our goal was not to produce the best performing model in terms of accuracy, but we focused on increasing the speed with which we can infer with these models. But of course, we have reference accuracies, just pay attention to relative difference, not to absolute what we achieved. So here, first, we did a baseline test to figure out.
The screen is not, I mean, I don't know if it's only me, but I can't see the screen anymore.
Yeah, I've lost the screen as well. I can't seem to get it back.
I'm sorry, that was my fault. Okay. My bad, sorry. I adjusted the host management because otherwise everyone can share their screen now.
Okay. Cool. All right, so we're back on track. Right, so we basically first created this baseline test, which gave us an indicator of where we currently stand. And we tested this on a desktop-grade GPU that's right here next to me. Was easiest to do this. So basically, we tried the base PyTorch model. So the model that we train is trained with a framework called PyTorch, and it is without any optimization, without any conversion. So just the raw model that we get. And these are the inference times that we get with them. So for example, for YOLO v5 nano architecture, we get 1.9 milliseconds of inference time, which is quite good. And for YOLO v5 small, we get 4.6 milliseconds. Small is a larger architecture than nano, which can also be seen below, given the accuracy that they achieve on the new dataset prepared for poacher detection. And you can see that nano basically has 0.46 MAP, very precise metric. And YOLO v5 small has 0.51, which is about a 5%, 10% difference, sorry. And the significant thing to look at here is that if we use a smaller architecture, we will already have a 41% difference in inference speed, while only losing about 10% difference in accuracy. For this data set, these accuracies may seem quite low, but again, in terms of absolute accuracy, this model is not properly trained, so we shouldn't really compare this. But the important thing is relative numbers here. So for our architecture and image size performance test, we basically compared multiple image size inputs, and we compared two architectures mainly. And we learned that YOLO v5 small using image size 640 by 640 is optimal balance in terms of inference speed and accuracy, as you saw on the previous slide. And performance of YOLO v5 nano on same image size is better than reducing image size input into YOLO v5 small. So for example, here we keep the accuracy MAP 046, while if we input smaller images into the smaller architecture, the small architecture, not smaller, small, we get 0.45. So YOLO v5 nano is a better option if we want to reduce image size. And also YOLO v5 9 on smaller image size is best if we want to prioritize inference time. So for example, if you're flying a drone out first and you just want to get some detections to see if there is something happening and want to save on power, maybe you can use this model first. And once detections start showing up here and you want to be more accurate, you can then switch to a larger model, which will give you more precision. I would also like to point out that this is not just a result of the architectures, but also the fact that poachers on the video are actually very small. So if you take the whole frame, poacher is just a part of the frame. And as you can see here in the comment that I put, we have poachers that are less than 3 pixels in size if we reduce image size. That's why it is also practical to use 640 by 640, because poachers remain big enough on those images. Then for the next step, we looked at mixed precision. As mentioned before, it is basically reducing the size of the number. So instead of floating point 32, we use floating point 16. And there is also an option to use integer 8, which is one small number. And again, we compared YOLO small and YOLO nano. And what you can see here is that this reduction from 32 to 16 doesn't really reduce the accuracy of the models, but increases the inference speed significantly, which is great and indicates that we should definitely use FP16. But unfortunately, we found that Jetson Nano does not have hardware acceleration for integer 8 precision, which we were hoping to use, because by using integer 8 precision, we would probably get even much better inference speed, but also suffer some drop in accuracy. So the only option really here is FP16, because we don't lose anything, but it gives us a huge boost in inference time. So you can see here, for example, for YOLO V5 small, it already increases inference time by 100%, which is great. To summarize, best architecture to use is YOLO V5 small, and image size is 640 by 640, which is also the size of the dataset due to poacher sizes and the accuracies that we've measured, and dropping the precision to FP16. But with a small note, this is also, of course, on the current dataset, so it may not hold for datasets that are created in the future. And then we tackled model pruning to try to further increase inference speeds by trying to reduce the weights, those weights that don't influence the precision too much, to 0, for example, and also try to get rid of some connections in the network so that we would have less operations to calculate. But we found that basically 2 different pruning approaches didn't really give us a speed up here. We tried PyTorch unstructured pruning, which is inherently supported. And basically the goal here was to get at least a smaller model so that it would take less memory, but it didn't happen. And also the authors of the YOLO V5 models had the same experience, basically no reduction in model size and also no speed up. And then we tried another approach from SparseML, which kind of prepares recipes for sparsification of models, and they try to figure out the best way to sparsify the model by hand specifying which parts of the model we should remove and which weights we should try to reduce, and also replacing the training strategy, which should produce a faster model. And then again, unfortunately, we didn't really get a speed up, as can be seen here. So for YOLO V5 small, this is the base PyTorch model measured on CPU this time, achieves 207 milliseconds per image, while sparsed model achieves 213 milliseconds, which is actually a bit worse. And these results were repeated through multiple tests on separate experiment setups. So it's not just this experiment, but apparently pruning here doesn't really give us a boost. We tried also to optimize the models with Onyx, which is a framework that tries to sort of unify different frameworks. So there are different frameworks like PyTorch, TensorFlow, etc., and it tries to convert a model into a model that all those frameworks understand. And while it does that, it also has an optimization framework, which we tried out. And as you can see here, for CPU, for example, using plain Onyx runtime, we achieve 104 milliseconds per image inference. And then furthermore, if we use deep sparse, which is again a recipe based engine by Neural Magic, which also prepared those recipes for sparsification, it reduces the inference to 45 milliseconds, which is quite nice. But unfortunately, we observed this effect only on CPU, which is not strange for deep sparse because this is a CPU-focused optimizer. But for Onyx runtime, it is in fact slower than running native PyTorch. So this was also not what we were looking for. And then finally, we performed experiments with Tensor RT, where we had the most success. And here you can basically see some quite impressive numbers, I would say. And we basically ran Tensor RT conversion on the nano and small architecture. And here you can see we used two precision modes, floating point 32 and floating point 16. And the difference here is quite significant, especially for YOLO v5 small, which gets 1.5 milliseconds of inference time per image when using Tensor RT FP16. And on the bottom here, you just see as a reminder that the default model we started with is 4.6 milliseconds. So this is almost 2.6 times improvement. And furthermore, we then put these models on Jetson Nano, and we did some experiments with Jetson Nano so that we have a nice summary of what all the different models can achieve. And for example, YOLO v5 Nano converted to Tensor RT using floating point 16 precision mode gets 25 FPS, which is quite good. Remember that we sacrifice only about 10% accuracy, and we are way faster here. Then we have a sparsified YOLO v5 small, which achieved 8 FPS. And the surprising fact here is that non-sparsified model, YOLO v5s, that we used as a final model from the previous iteration of the challenge, actually achieves higher frames per second, and the result is 13. And this is still the best result that we've obtained. And for reference, we also compared it with larger architectures, which have better accuracies, just in case that super precision would be needed. And for example, the largest model we tried is YOLO v5 large, reaches 2 FPS on Jetson Nano. More good news is that even if we use the 5-watt mode, so as you can see here, CPU 3 and 4 cores are disabled, and we downclock a bit so that we save power and are able to run it as a USB accessory, basically, we can still get 5 FPS on YOLO v5 small, floating point 32, so not quantized yet. So basically, if we quantize it to FP16, we would get even more performance here on very low power mode, as opposed to using the full power of the Jetson, where we can achieve about 8 FPS using non-quantized model. So this is really good news because it means that you can conserve power while still getting relatively good frames per second of inference. So as a conclusion, we should use YOLO v5 small because it is the optimal balance of accuracy and inference speed. Image size should remain 640 for the current data set because poachers remain big enough. And we can use this image size on YOLO v5 small for accurate predictions and this image size on YOLO v5 nano to get to the first detections of poachers with conservation of power. We should definitely use floating point 16 precision because it doesn't cost us any accuracy, but it definitely gives us an increase in inference speed, which is great. And for the Jetson Nano, it seems like that Tensor RT is the best choice out there. We were not able to match it with any other framework. And also, if we look at the CI/CD part of it, automation is much easier if we use Tensor RT, because we found that all the other frameworks that we tried come with a significant number of dependencies that need to be installed and dragged along, as well as some of them require modifications to actual architectures, which means that it is not as easy to follow updates that are happening in the industry. So for example, if YOLO v5 architectures are updated, it means that we would have to go and change the code a bit to be compatible again for conversion, which is not ideal. But if we stick with Tensor RT, currently it is quite straightforward, and if a new release comes that is faster, we can still use this without any damage to automation. And the next steps, so as you saw in the presentation, we were quite focused on testing on Jetson Nano, and the results may be different if we were using also other accelerators, but it seems like that for NVIDIA hardware, Tensor RT is definitely the way to go. And if we have different hardware accelerators, we can again retry all the other optimization techniques. Most importantly, however, I think that it would be really good to perform actual on-drone tests to see how much power we drain and how fast the inferences actually need to be, so that we can also define smart goals for model optimization. Smart being, you probably all know what it is, but the thing that I think would be really useful here is to be very specific, to have an aim that we should achieve. And then we can also do maybe some hand-based pruning, which is the next point, so that we would structure the pruning and write our own pruners for the architecture. And here I also wrote in the parentheses, YOLO v5 is actually quite up to date, and with every release, they also release some improvements to the architecture itself. And that gives us already some inference speeds, which we also proved in our tests, because the sparsified models actually use a slightly older version of YOLO v5, and they are slower than the newest models that aren't sparsified. Thank you for your attention. So if you have any questions, hopefully we can answer them.
I believe Bram has a question. He raised his hand.
Yes,
All right.
true. Thank you. Can you hear me correctly?
Yep.
Okay, nice. Thank you for the very nice presentation. It was very interesting to hear. And I'm doing research on efficient neural networks myself. So I was wondering about the sparsity levels that you use. What is the actual percentage of connections that you removed?
So the recipes aim for 80% sparsity. But we also tried some more hardcore sparsification using the unstructured pruning supported in PyTorch. There I ran it with 50, 75, and 95, but no solid results there. Also, if you're interested in that, I invite you to also check the YOLO v5 repository, where there was some discussion on sparsification. And they actually also didn't get any boost, but there were some ideas that were a bit more complicated to get there.
I wanted to ask you, how do you know how they implemented it? Because in the research papers that I've read so far, many of them only do this like in theory by masking the weights and setting the weights that they don't use to 0, but they still have this full matrix of weights that's going through the CUDA.
Exactly, yeah. That's the problem. Yeah.
And that's why it doesn't speed up anything, and it's still only in theory.
Exactly. Yeah, so there are multiple implementations there. I think 3 popular ones are basically just, first one is just setting those weights close to 0 to 0. Second one is looking at how gradients flow through, and in correlation with weights, set those that gradients don't pay particular attention to, also to 0. And the third one is to also check during training how the ways that you're changing are affecting loss functions. This one is the most sophisticated one, and then sets those to 0. But as you mentioned, the real problem there is that the tensors don't change, right? And that's what should be tackled. But like I said, in the end, if you do that, if you change tensors, you immediately are not compatible with what's been happening in the repositories where you took the models from. And that's a problem because it ruins your automation, and it also forces you to keep updating when there are updates on those repos, right? So more work for you.
Yeah, great. Thanks. Can I contact you later? Could you put your chat maybe? That would be awesome.
Sure.
Thanks.
All right, thank you, Jaka, and the whole team for your awesome effort. I think it was a great presentation, and thank you for all your hard work. I believe there are no more questions for this team, so I think we can head on to the next team. We have here Aisha Kala for the CI/CD team.
I had a question right in the beginning with regards to the presentation on the YOLO V5 small. Something was mentioned about the frame size 640 by 640. Our cameras capture at 640 by 520 at 60 Hertz. I'm not sure how much of a bearing that has on the model that the guys were using, but I would assume that is possibly changeable if necessary to a slightly lower frame density if you want, or pixel.
Yeah, so it's not a problem the way it's right now.
Okay.
It is generally neural networks that you supply an image that is equal in both sides, and there are some good techniques to resize images that don't adhere to that. So it doesn't really hurt if one side is smaller than the other. It resizes. But yeah, reducing the frame rate makes sense if it puts less strain on the whole processing system, because we will probably limit the frames entering into the model anyway. So for that side, it's taken care of. But if reduction in frame rate makes the whole thing heat less or use less energy, then it's beneficial, because we will not need 60 Hertz, that's for sure. None of the models achieve that kind of performance in our tests.
Okay, thanks a lot for that. I just want to plug in my charger before my battery dies here.